Okay, hello everyone and welcome back to part 2 of our lecture on hash tables. In the first part, we covered the fundamentals of hash tables, including how they work, common operations, and the concept of hashing with various hash functions. We also discussed handling collisions through techniques like chaining and explored considerations for designing effective hash tables. Now in part 2, we are going to dive deeper into advanced topics. We'll look at alternative collision resolution methods, performance considerations, real-world applications, and how to optimize hash tables for specific scenarios. So let's get started. Now, we'll look at function pointers, which is a type of pointer that holds the address of a function instead of a data value. This allows us to use the function pointer to call a function indirectly, meaning that we can execute a function by calling the pointer itself rather than the function's name. In the context of hash tables, function pointers allow us to pass different hash functions to the hash table implementation. And depending on the specific needs of the application. This flexibility is especially useful if we want to experiment with different hash functions, or if we are dealing with various data types that require unique hashing approaches. So by using function pointers, we can design a more adaptable hash table that isn't limited to a single hard-coded hash function. So it will be more versatile and reusable. Now, here is an example of a function pointer declaration, which will help you clarify the syntax. Now here we have float, then inside the parentheses we have star, function pointer, and then string. Now let's break it down. First we have float, which specifies the return type of the function that function pointer will point to. In this case, it indicates that the function returns a float. Then next we have a star function pointer inside the parenthesis, which is the function pointer itself. And function pointer is simply the name of the pointer. Like any other pointer, you can choose a name that's descriptive of its purpose. Then it will be easier for you to see which to relate the name with the function. Then we have string, which indicates the parameter types of the function that function pointer will point to. Here it's function that it's a function that takes a string as an argument. So with this syntax, function pointer can hold the address of any function that matches this signature, one that returns a float and takes a string as a parameter. We can then use function pointer to call that function indirectly, making it useful for flexible and modular programming. Okay, now here we are continuing our discussion on function pointer, and then in this example we are using the same example where the parentheses around star function pointers are necessary. They define function pointer as a pointer to a function rather than as a function returning a pointer. So without these parentheses, the compiler would interpret function pointer differently, leading to errors in your code. The correct syntax makes it clear that function pointer is specifically a pointer to a function that takes a string parameter and returns a float. Now Here, the float at the beginning specifies the return type of the function that function pointers can point to. This means that if any function assigned to function pointer must return a float value. Specifying the return type in this way ensures that the function pointer is compatible only with functions that match this signature. Now here, float at the beginning specifies the return type of the function that function pointer can point to. This means that any function assigned to function pointer must return a float value. Specifying the return type in this way ensures that the function pointer is compatible only with functions that match this signature. Now here the string part defines the parameter list for the function that function pointer can point to. In this example, we specify that the function pointed to by function pointer must accept a single parameter of type string. Now we have seen how to declare a function pointer for a function that returns a float and takes a string parameter. But what if we need a function pointer for a different function signature? For example, what would a function pointer declaration look like if the function it can point to has a void return type and accepts two integer parameters? In this case, the function pointer declaration would be written as void function pointer integer and integer, so two parameters. Now here if you look at this one, this is the example of how we can have a void return type and then it accepts two integer parameter. Now we have void function pointer and then integer, two parameters. Now here's the breakdown. Void specifies that the function returns no value, and that function pointer is the function pointer itself with function pointer as the pointer's name. Now integer and integer indicates that the function it points to should take two integer parameter. So here you will see we have declared void fp int, a function pointer that points to functions with a void return type and two integer parameter. Now take a look at the foo function here. This function matches the signature of our function pointer fp. It accepts two integer parameters and returns void. Inside foo, if it simply prints the value of a and b. Since foo has the correct signature, we can assign its address to fp and then use fp to call foo. This allows us to dynamically choose which function fp should point to at runtime, giving our program more flexibility. If you look at here, cout, we are printing a is a and cout b is the value of b. So we are taking this void foo function is taking two parameter, and then we are just so this function that fp can point to. Now that we have our function pointer declared, let's look at how to assign a function's address to it. Here we have void fp integer. This is our function pointer, which can point to any function that takes two integer parameter and has a void return type, as I said. Here we have a function foo that matches this signature. And now to assign foo to fp, we simply write fp equal to foo. That is what we will write. just to this is the address of foo which is assigned to FP like this. This line assigns the address of foo to FP, so now FP can be used to call foo. This assignment makes FP point to foo, allowing us to invoke foo indirectly through the function pointer. This flexibility is particularly useful when you want to dynamically assign different functions to a pointer based on runtime condition. So once the address of foo has been assigned to FP, the foo function can be called using FP like this. Now, calling FP 5 and 10 will invoke foo with the arguments 5 and 10. This results in foo executing and printing A is 5 and B is 10. Using this FP to call foo provides us with flexibility. We can dynamically assign different functions to FP at runtime and call them in this same manner, making function pointers a powerful tool for modular and adaptable code. Okay, now let's discuss how we can use function pointers in designing a flexible constructor for a hash table. Now first, the client designs their own hash function based on their specific requirements. Once they have this function, they pass its name as a parameter when creating an instance on the hash table. Then second, the hash table constructor then accepts this parameter as a function pointer, allowing it to reference the client's custom hash function. Then inside the constructor, we save the address of the hash function to a function pointer in the private section of the hash table class. This ensures that only the hash table itself has direct access to the hash function, maintaining encapsulation. With the function pointer stored, the hash table can now use it to call the client's hash function whenever needed. This setup allows us to customize the hashing logic for different applications without modifying the hash table's core code. Okay, now here we have a section of the hash table header file. We have hashtable.h, the header file, which includes the class definition and function declarations. First, we see to include directives for linklist.h and array.h, which indicating that our hash table will use linked lists and arrays as part of its implementation. Then the class is templated with class data type, making it flexible to work with different data types. Then in public session, we have the constructor hash table integer hf, constant data type, and integer s. This constructor takes two parameters, hf and constant data type. This is a function pointer to the hash function, allowing clients to pass in their own hashing logic. Then second is integer s. So these are the two parameters. Integer s is the size of the hash table. So next we have a set of core functions for managing the hash table. We have bool insert, bool retrieve, remove, update, and make empty. So next we have private section begins with the declaration of a table, array, linked list, data type, table. Here the space is necessary. So this line creates an array of linked list objects where each linked list holds elements of type data type. This setup provides a structure for chaining, which is a common technique for handling collisions in hash tables. Next we have the function pointer. integer hash function constant data type. This function pointer hash function holds the address of the hash function provided by the client. It takes a constant reference to data type and returns an integer, which will be used as the index in the hash table. This flexible design allows different hash tables, different hash functions to be used, adapting the table's behavior as needed. Finally, we include the hashtable.cpp, which is the implementation file. This inclusion connects the class declaration with its implementation, ensuring that the function definitions in hashtable.cpp are linked to the class. So this private section encapsulates the table structure and hash function, keeping them protected from external access while allowing the class to use them as needed for efficient data storage and retrieval. Okay, now let's talk about the clientele or audience for the hash table class. First, we observe that the hash table class utilizes both the linked list and array classes. These classes are likely part of a larger library or code base, providing foundational structures that make our hash table implementation more efficient and modular. When we create a class like hash table, the clientele extends beyond the immediate team of programmers. It's important to design the class in a way that's accessible and adaptable, not only for the main developers who directly use the class, but also for others who might integrate or extend this functionality in the future. The clientele also includes developers who may write additional classes that depend on or work with hash table. This could include developers building more complex data structures or utilities that rely on efficient data storage and retrieval. So we can say that when designing classes, we should think about making them user-friendly and well documented, keeping in mind that a broad range of programmers, present and future, may rely on our code. So now let's take a look at the constructor for a hash table class. This constructor is templated. The constructor is templated to support different data types, which allows the hash table to be used flexibly with various data structures. In the parameter list, we have integer, HF, then constant data type, and then integer s. These two parameters. The first parameter points, the function pointer represents the hash function that the client passes in. It takes a data type reference and returns an integer, which we will use as the hash index. And then second, the integer x is the size of the hash table. Then on line 4, we see table s. Here table is initialized using the array constructor with size s, effectively creating an array of linked list objects, each capable of holding elements of type data type. After that, we have hash function. In the constructor body, we assigned hf to our hash function pointer. It says hash function equal to hf. This line connects the client's custom hash function to our hash table class, enabling the hash table to use the client-defined hashing logic. Now, by passing the hash function and table size as parameters, this constructor offers both flexibility and control, allowing client to tailor the hash table to their specific requirement. Okay, now here if we go more deeper, we notice an important detail here. In the initializer list with table S, the data type for array is actually linked list data type. This means that while data type in hash table refers to the data type of the items that will be stored, array itself holds linked list instances as its element. Essentially, the array is an array of linked lists, each capable of holding elements of data type. This structure is key to implementing the chaining method for handling collisions in the hash table. Instead of storing data type objects directly in array, we store linked list data type, allowing each index in the array to maintain its own list of elements that hash to the same index. Now, by passing S as the size to the array constructor, we ensure the hash table has the necessary capacity to store our linked lists at each index. Okay, so here when we call table S in the initializer list, it triggers the array constructor to create an array of size S. This array doesn't hold simple data types. Instead, it holds linked list object. What happens here is that for each position in the array, a linked list constructor is called to initialize each element as a linked list data type. This setup is crucial for the chaining technique to prevent collision, as I said. By having each array element as a linked list, we are prepared to handle cases where multiple keys might hash to the same index. So each linked list can hold multiple entries that share the same hash index, allowing us to resolve collision effectively. Okay, so now let's go over the insert function for our hash table class. Here we have, so we start by calculating the hash index for new object by passing it to hash function. This gives us the location in the array where the object should go. Now next we will do bounds check. Before inserting, we perform a bounds check. If location is outside the range of the table's length, the function returns false, indicating a failed insertion. Otherwise, so then it insert. If the location is valid, we use table location dot insert new object here. And then table location refers to a linked list at that specific index. By calling insert on this linked list, we are effectively adding new object into the correct chain for that index. Then finally, if the insertion is successful, the function returns true. Now then we are so just like the insert function, we first determine the index or location by passing the retrieved object through hash function for the retrieve section to retrieve any value. Then we perform a check to ensure that location is within the valid range of the hash table or not. If the location is out of bounds, the function immediately returns false, indicating the object cannot be retrieved. Then, assuming the location is valid, we attempt to retrieve the object from the linked list at table location. The retrieve function of the linked list class is called here to find the retrieved object. If the retrieve operation fails, we return false. Then, if both the location is valid and the retrieve operation succeeds, the function returns true, indicating successful retrieval. This approach to retrieval leverages chaining. Each location in the table is a linked list that may hold multiple elements, allowing us to manage collisions effectively. Now let's look at how the remove function works. We start by passing the removed object through the hash function to determine its location within the table. Then we verify the location is valid or not using the bounds check. Then if the location is valid, we attempt to remove the removed object from the linked list at table location. Here we rely on the remove function in the linked list class. If it fails, we return false. If both the function is valid and the removal is successful, the function returns true, signifying that the object was successfully removed. Okay, now update. So first the update object is passed through the hash function to get its location within the hash table. Then we ensure that the computed location is within the valid range of the table's length, otherwise return false. Then at this location we check if update object already exists in the linked list. This is done using the find method in the linked list class. If the object isn't found, the function returns false. If update object is found, we proceed with the replacement. The replace method in the linked list at table location replaces the current object with update object. Then the function returns true if the update was successful. Okay, now this one is make empty. So first the function is defined as void since it doesn't need to return any value. Its purpose is simply to empty the hash table. The function uses a for loop to iterate over each index in the table. The loop starts at 0 and continues until it reaches the end of the table determined by table.length. Then for each index I in the table, it calls make empty on the linked list object stored at table I. This ensures that each linked list in that table is cleared, removing all elements within it. Now finally, by clearing each linked list, this function effectively empties the entire hash table, making it ready to be reused or reset. Okay, so here there is a code using hash table. So it demonstrates how to use the hash table class with specific hash functions and table sizes. We'll just go through this code. So first we have the header file hashtable.h. Then we have structure, my structure. Inside we have string that will be the key for us. Then we have number, integer number, and then bool operator, assignment operator. Okay, next here this operator, it is necessary to overload the assignment operator for the linked list functions here. Now in the actual code, a comment is placed above hash table telling the client that this is needed and what is required. Now here if you see, we have constant integer size 1 equal to 97, size 2 equal to 199. These two specify the sizes of two different hash tables. These values are typically chosen to be prime numbers, as prime numbers can help reduce collisions in a hash table. Then we'll declare the hash function integer hash 1, integer hash 2. These are declaration for two different hash functions, hash 1 and hash 2, which take a my structured object as a parameter. Each function is expected to return an integer that will represent an index in the hash table. The specific logic for these functions is not shown, but they should generate a unique index based on the data within my structure. So basically this code demonstrates how to set up two hash tables, h1 and h2, with different hash functions and sizes. And then each hash table uses a unique hash function which provides flexibility in how objects are indexed in the tables. This setup allows for experimentation with different hash functions and sizes, potentially helping to optimize hash table performance depending on the use case. Okay, here my structure, my object creates an instance of the structure named my object. First insertion, we will do my object dot string equal to elephant, and my object dot num equal to 25. So we are inserting one string and one integer value. Set the string and num fields of my object. Then h1 dot insert my object inserts my object into the first hash table h1 using the insert method, then modifying and inserting into second hash table. The value of my object are changed. My object dot string equal to giraffe now, and my object dot num equal to 50. Then we are inserting it to the the modified my object into the second hash table. Then here it returns 0. Then we have integer hash1 defines a function hash1 then that takes a constant reference to a my struct object and returns an integer. Then we have integer sum equal to 0, which initializes a sum variable to store the cumulative ASCII value of characters in the string field. The for loop iterates over the function over the first 3 characters of object dot string or fewer if string dot length is less than 3. So for each character, the ASCII value is added to sum. Then the hash value returns sum size 1, which returns the hash value by taking the remainder of sum divided by size 1. This ensures the hash value falls within the bounds of the hash table size. So the hash table ADT description is very close to the list ADT description. The only items missing from the hash table ADT description are an iterator, a function to determine when the list is empty, then find to determine whether an element is in the list, and a current position. If we had all of these, we would have a fast list or an enhanced hash table. So everything would be easy to implement for the hash table except for the iterator. The iterator is an important part of a list, so we would like it to be fast as possible. We can iterate through a collision list, but finding the next collision list to iterate through might not be so fast. So we'll now see an example of an iterator. Here, if you see, we have this large gap with empty linked list. Instead, we can have a linked list run through the collision list so that the linked list contains every element. Then iterating through the linked list is simple and fast. So here are the complexities for list entity. So for insert, we'll insert at the head of the linked list. The complexity is theta 1. Then iterator, each step will be theta 1. Then for find, element is found by hashing, so it is theta 1. For uniform hashing, the hash function and hash table are designed so that the length of the collision list is bounded by some small constant. Then for retrieve is theta 1 for uniform hashing, and there are more if we see here replace, which is theta 1 using the current position, an operation to determine whether or not the list is empty, which is theta 1 because we just test the linked list to see if it's empty. Then an operation to empty out the list is theta n, the best we can do since each node must be freed. Then remove to make this last operation as fast as possible, considering using a doubly linked list for the linked list. Now let's see what is doubly linked list. The description for the doubly linked list entity is the same as that for the list entity. We don't consider implementation in the edit description, and double links have to do with implementation. The implementation of the doubly linked list using the hash table is also not a part of the entity description. So to avoid special cases, we'll have a header node and a trailer node in the doubly linked list. Few data structures use arrays of doubly linked list. If such a use arises, we could create a doubly linked list without header and trailer nodes to avoid wasting memory. So we will now see an example here of a doubly linked list. If you look at here, we have a hash function, and this red line is the doubly linked list. So we have header and trailer if you look at here. Now let's start to see in detail what exactly is doing. So if you see here, we have 0 to 10 memory indexes, and then so let's start here. If you see, each node has 3 pointers, not just one. If you look at 36, it has 3 pointers. It is pointing to 3 sides. It is pointing to 99, it is pointing to 70, and it's pointing to 47. The elements were inserted in this order, like 33, 65, 63. So first it was inserted 33. 33 is the first one inserted. Then it inserted 65 here. Then it is inserted 63, this one. So as you already know from the part 1 of our hash table lecture, we did a total clean example. We saw an example of how an hash table works and assign using the hash function. So this is how these numbers are assigned using that hash function. This is the hash function here. So using this hash function, these values are inserted into these assigned locations. So here if you look at here, 33 divided by 11, there is no remainder. The remainder is 0 here. So this 33 is inserted into 0 index. Then for 65, the remainder is 8. So it's 65 divided by 11, the remainder is 8. So it's 10. So it's inserted into 10. Then for 63 it's 8, so it's inserted into 8. For 31 it is 9, so it is inserted here. So for 53 it is also 9, so it is inserted. So the 31 moved aside, and then 53 inserted. Then 22, here 22 by 11, the remainder is again, the remainder is 0. So then 33 moved, and then 22 inserted. Then 47, here the remainder is 3, so the 47 is inserted. Then 99, again on the remainder is 0, so it is inserted here. Then 36 here on 3, and then 70. So this is how in the elements were inserted in this order. Okay, since each node is inserted at the beginning, you will see these nodes from tailor to header. So now if we want to insert 52, the hash function gives us index 8. Now here, this one, so 52 is inserted at the beginning of the collision list there. So 63 will move, and then we'll add 52. The new node 52 must also be inserted at the beginning of the doubly linked list. So then the header will be added to the last one added. The first, before the header was connected to 63, because 63 was the last one inserted. Now that we have added 52, now header will change to 52. The new node 52 must also be inserted at the beginning of the doubly linked list. And then now if we want to remove 31, let's say we want to remove 31, so 31 is on index 9. The hash function gives us index 9, so where we will find 31. So node 53 contains the pointer to it. So node 53 is pointing to 31. So here 31 can be removed from the doubly linked list in theta 1 time. So 31 can be removed from the doubly linked list. So 31 is also removed from the collision list using linked list removed. Okay. The order of the doubly linked list can be maintained independently of the singly linked list. If we wanted a sorted doubly linked list using the same insertion order of the elements, it would look like this. So we'll see, this one is a sorted example. So if you look at here, we have a same hash function. Now if we try to insert 52 here, the function gives us index 8. So we are moving 63, and then we are adding 52 here at the beginning of collision list there. Now 52 must also be inserted in the doubly linked list. However, it would take theta n times, since its position in the doubly linked list must be found. Now if we want to remove 31, it's giving you the index 9. Now in theta 1 time, it is also removed from the collision list. So we have to consider memory for that. So each node has 3 pointers now. So we have template class data types, structure node, we can have node data type next, node data type DL next, DL back for the collision list. And for the doubly linked list, we can have DL next, DL back. So if there is only one node in the collision list on average, then the linked list used for each element also has 2 pointers, start and current. This gives us a total of 20 bytes of wasted memory per node. So if each element is 20 bytes, 50% of memory is wasted. However, if each element is 980 bytes, only 2% of memory is wasted. Element size is an important consideration. Now, in order to make the implementation easy, we'll have to make some changes to the linked list class. It will become a specialized helper class for the doubly linked list. Now what changes we'll do? We will change the name of the class from linked list to collision list, modify the node struct so it has the 3 pointers we need. We need a function to retrieve the current pointer called getCurrent. Instead of eliminating the current position when we insert a node, we'll set the current position to the node we inserted. So now we'll also make some changes to the hash table class too. It will again be a specialized helper class just for use in the doubly linked list. Now we will rename the hash table class to DL hash table, short for doubly linked list hash table. Then keep the location used throughout the class as a private data member, having a function getCurrent which retrieves the current position of the collision list that was used in the last use of location, that is return table location dot getCurrent. Then we'll also need some functions which are convenient for the copy constructor and deep copy. Get hash function which will return the hash function pointer, set hash function which will set a hash function pointer, get size and change size. Okay, now look at this header, this code in for doubly linked list dot h the header file. Here we have another iterator. We added another iterator, bool last and bool get previous, inline bool get previous. These two new iterator we have added. Then we have added these two new header node and trailer node. These are the static nodes not made in the heap. Then the header will point to header node here, and the trailer will point to the trailer node. Now we don't really need the header and trailer pointers, but without them the code may be confusing. And without header, we would access the first data node with header node dot DL next. And with header, we would access the first node first data node with header pointer DL next. So with this private section, do we really need a destructor, copy constructor, and overloaded assignment operator? Yes, there can be pointers to dynamic memory here. For example, header pointing to next. Sometimes pointers to dynamic memory are hidden. So here we have the constructor. When current is set to the trailer node, it means there is no current position. This is the destructor here. Now when insert in the collision list is eventually used, it now makes the inserted node the current node. Now this function eventually calls getCurrent in the collision list, which returns the current pointer there. So the address of the node that was just inserted is assigned to the different current pointer here. Then we have this if you see in the table in showing how insert works, so we'll use this convention for the parts of node. Okay, now here if you look at this diagram, just for you to understand properly, the current node has been inserted into the collision list. If you look at line 38 of insert previously, here we'll start, we have header, we have current, we have collision list, we have doubly linked list. Now if you look at here, however, it still needs to be placed into the doubly linked list. If you first use this current pointing to doubly linked next equal to header pointer DL next, it is if you look at the diagram here, the current is pointing to doubly linked is next. So we have this arrow here which is pointing to doubly linked list. Next, this line is using which is making this which is pointing doubly current pointing to DL back equal to header. Now this is the one which is doing, so the current, the middle one, the black one, which is the current one, is now pointing to header with this red arrow. Now third one here, we are doing header pointing to DL next pointing to DL back equal to current. So this is what this one is doing. So the header pointing to DL next and DL back. Now this one is doing the header pointing to DL next. So now the header is pointing to DL next, which is the current one, which is everything is now equal to the current. So if you look at here, basically after doing all of these things, lastly the header pointing to DL next means it is pointing to the current. Now current has been inserted into the doubly linked list, and there won't be a current position in the doubly linked list after the insertion. The client is using the doubly linked list, and this is what the ADT describes. Okay, now this is just the implementation of the first. We have template class data type, then the bool doubly linked list data type, then first data type and list EI. We have a condition if header pointing to DL next equal to trailer, then return false, and then the current is set to header equal pointing to DL next, and list EI equal to current pointing to info, and then if everything is good, it returning true. Next, it is the get next. So I hope you're understanding, because I'm just go through I'm just making it short because I already explained this type of implementation before in detail. So that's why I'm just doing it in short, so that I hope you already know what these codes are doing, because I already have I already explained in details in big like similar functions before in hash tables also. So we have this get next function here, and then we have last, and then get previous, find. So here if we pass in element here, retrieve will change the value of it, which will give us an error in find. We are not supposed to retrieve. So element is copied to EL first, then passed into retrieve. Okay, then remove sets element before it is removed. and then also sets current to the node that element is in. Then it removes current node from doubly linked list. Okay, now we'll do a demo of the remove also, how it works for these two lines. First, start with this line 126 where it is saying current pointing to DL back, DL next equal to current pointing to DL next. So that means first current first is it is pointing to doubly linked list, then it is pointing back. Now we have current equal to trailer, so current it means trailer here, and then table dot remove the element is in the node current was pointing to, so this one is gone. Now then it returns true. Now we'll do replace and is empty and make empty. So I've already gone through these functions before in detail. It is just for doubly linked list. You can go through. If you don't understand any line or anything, you can let me know.